Hello and welcome to this week 7 for lecture 1 in radio astronomy. We will start a discussion this week on something called coordinate system. Now, what is a coordinate system and why do we need it? I mean, of course, the entire approach of astronomy is to detect celestial object on the sky, and we need to know how to locate those objects. How to locate those objects, the stars, the galaxies, when they are supposed to be up, when we should point at the telescope towards which part of the sky, and whether it is observable from our given location on the Earth. As we know, depending on whether you are in the northern hemisphere or southern hemisphere, certain parts of the sky are not visible to us. So that's whole discussion we will start today with emphasis on something called coordinate system, which is very important to define a coordinate system as we start the discussion on where to point the telescope, when to observe a particular source, etc. So often, if you see this kind of a blurry image, okay, it's a time-lapsed image where you have kept at the telescope site, okay, and you've seen the sky which goes around because of the movement of the Earth. We will come back and explain this figure in a bit, but this is quite a well-known feature. It happens because of a large time lapse which captures the movement of the stars in the sky. Similar thing is also noticed in case of like this analemma, where if you are in a particular position on the surface of the Earth and you keep looking at the sun, or take the sun's image every day at the same time across the entire year, you will see that the sun will make kind of a figure of 8, but a little bit skewed, kind of a projection on the sky. And again, this is again because of the movement of the Earth with respect to the sun. Depending on where you are on the surface of the Earth, you can see various time-lapse images showing variety of pattern. It basically means that you are at different parts of the globe. These things are not exactly in the same location. They are in different parts, and they are capturing a time-lapse movement of the stars across the sky. The primary reason for this is the movement of the Earth, the rotation, the revolution, the tilt, the tilt with respect to the ecliptic plane, and so this is the particular picture of the Earth which is moving around the sun and with its own tilt and which causes seasons, but also which causes this variety of movement of different stars, galaxies on the sky. So continuing on the same line, if we can, from the perspective of the Earth, if the observer is on the Earth, so with respect to the Earth, you can see this solar declination changing across the entire year. Okay, so it makes some kind of this S kind of a curve with respect to its position from a fixed point on the Earth, which is partially because of the Earth's rotation about its own axis and around the sun, the revolution. This is with respect to the Earth. So if an observer is on the Earth, it's much easier to assume that there is a celestial sphere, and on the celestial sphere every star has a coordinate, and that kind of moves with respect to the Earth. And so that coordinate system or different coordinate system based on the celestial sphere is how we can track a star or a galaxy or a celestial or a cosmic source on the sky. So we'll come to the discussion in the later slides. Just to explain this particular image, if you have a telescope, an optical telescope, and you point towards the north celestial pole, if you're in the northern hemisphere, and so if your axis is around parallel to the polar axis, then you, for time-lapse image, will kind of give you this kind of image, which is exactly what the background one shows. Okay, so location is very important. Measurement of the accuracy, position accuracy of individual sources are also important. This is a list of different measurements done over the years, and you can see this goes down in terms of this AS is arc seconds, so seconds of an arc. Then MAS constitutes of milli-arc second and micro-arc second. So if you see, as we go from 1400 AD to 2000 AD, this entire thing has come down from thousands of arc seconds, which is kind of a few degrees, down to a few micro arc seconds. Okay, so that's a huge amount of precision which has increased over the years, over centuries, right? That's quite commendable. There's a few catalogs which are very famous nowadays, and you can see the different accuracy in positions which are available with us. So to increase the accuracy, exact location of the stars, the galaxies, the cosmic sources, we need to understand their coordinates accurately. We need to understand, we need to measure, we need to determine. So a coordinate system, necessity of one, evolves naturally, right? So as we motivated in the last few slides, that we kind of designed something called a celestial sphere. Celestial sphere is nothing but it's kind of a crater sphere on centering the Earth, where the center is the Earth itself, the center of the Earth, the center of the celestial sphere as well. And there are a couple of other things which has to be defined. First one is, if you locate an observer near point O, then if you're looking towards the sky, the location exactly 90-degree top, at the top of us, 90 degree from the horizon is the zenith. That is one definition. If you're looking towards the center, you define the nadir point. The horizon is 90 degree from the zenith. Okay, and so you can point towards different sources as a function of this elevation angle or azimuth angle from the position of the location of the observer. For definition, there is something called north celestial pole, which is the northern pole of the celestial sphere, and the south celestial pole in the same respect. The equator is near towards the 0 degree celestial latitude, and which positions itself with the movement of the sun, the celestial sphere. And so you can define the northern celestial pole, southern celestial pole, and any line which is joining this northern pole with the southern pole passing through the zenith is the meridian of the location where the observer is. So few things: the location of the observer. If you know that, then you can draw a tangent. This is the horizon for the observer. Anything below that, the observer cannot see at a given time. But thanks to the movement of the earth, the sky will keep on rotating around the observer. The vertically up top position pointing towards the sky is called zenith, and below is nadir. And the position of the sources across the sky can be measured in terms of the elevation and azimuth angle with respect to, of course, the north and the south pole. Okay, so yes, so now if you define the celestial sphere, which is counted for bigger sphere drawn on top of the earth, keeping the center of the earth as center of the celestial sphere. Now if you draw the celestial equator, it contains the sun's path around and the northern pole and the southern pole by itself. It's called the north celestial pole and the south celestial pole. Any line which is connecting the north pole and the south pole and passing through the zenith is called the meridian, local meridian. Okay, so that's pretty much what we need to know. So celestial sphere, just to recap, an imaginary sphere that rotated about an axis passing through the north and the south poles of the earth and intersecting the celestial sphere at the north and south celestial poles. Imagine the stars in the sky to be attached to the surface of this sphere. The ecliptic, the path of the sun with the respect to the distant constellations as observed from earth. The ecliptic is the line where the plane of the earth's orbit cuts the celestial sphere. Vernal equinox, twice during the year the sun crosses the celestial equator, once moving northward along the ecliptic and later on moving to the south. In the first case, the point of intersection is called the vernal equinox, and the southern crossing occurs at the autumnal equinox. So that's how we defined in the last slide. So in the vernal equinox, the sun intersects with this celestial equator and starts moving towards the north along the ecliptic and later on moving towards the south after crossing this at the autumnal equinox. The another thing which should be important is the solar time or synodic time. The solar time is defined as an average interval of 24 hours between the meridian crossings of the sun. It is the average time elapsed during which an object comes back to the same position with respect to the sun. There are few standard reference frames for position in astronomy. The place of observation, if that is the origin of the coordinates, then it is called topocentric frame. If center of earth is at the origin of the coordinates, then it is called geocentric frame. Center of the sun is at the origin, it's called heliocentric frame. Center of mass is called barycentric frame. If the local vertical is chosen as direction, it's called horizontal system. Celestial poles are chosen as pointing north and south, it's called equatorial system. And normal to the ecliptic is chosen, it's called ecliptic system. And a pole by convention is called One of them is called Galactic System. So we will touch upon ecliptic system, not ecliptic. We will touch upon Equatorial system. Horizon system. Will not discuss ecliptic, and we also touch upon galactic system for this particular lecture. So how to locate an object? Say if you have a sphere, a standard sphere, you just need what? You know the radius of the sphere. So you need the azimuth angle and elevation angle. So supposedly you draw a spherical polar coordinate system. You know that at a radius of r there is a sphere. So let me redraw. So if I need to point of P on the celestial, on the sphere, so say it is going across. Right? So the projection down here, this will cut a distance of theta, angle of theta, and an angle of phi with respect to the two axes, right? So x, y, and z axis. Okay, so if I know my distance r is already known because it's a sphere. If you know theta and phi, I can locate my object on the sky for a horizontal system. Okay, that's easy. What you have to remember is solar day is 24 hours. Arc spin period is a little bit less than 24 hours. And we have to define something called sidereal time. Typically, we use things like right ascension and declination, but we'll come one by one as we go through it. So the different coordinate system, equatorial we already mentioned, this we will be covering. Ecliptic we will not cover. Galactic we will cover, and also the horizon. So for horizon coordinate system, there is an altitude h, which is defined as the angle measured from the horizon to the object along the great circle that passes through an object, that object and the point on the celestial sphere directly above the observer, known as zenith. Azimuth is a, so you can define this way, or you can also define this as the previous slide we have done. This is theta, and typically what we say is phi. So the same thing which we drawn earlier, where you have x, y, and z. You have a point on the sphere drawn at a radius of r. So you have a projection on the x and y plane. It makes an angle theta with the z-axis and phi with the x-axis, and so on and so on. So if you know the altitude and the azimuth, you know the position of that particular source. This is called the horizon coordinate system. Easy to know the position of a star at a place from the given point of the telescope. But one drawback is that it varies from one position where the observer is to the next position. So it's very local, it's very relative, and so it is good for to know from the position of the telescope itself. But if you want to cross-check with another fellow observer. This is not the universal coordinate system. So if you define something more which is can be used by everybody from different parts of the Earth. So we end up talking about equatorial system, very widely used. It defined in terms of right ascension or alpha and declination or delta. It's almost synonymous, basically synonymous with what we say is like the longitudes are referring to the right ascension. So it's like the longitude of our terrestrial sphere, and this is like the declination is like our latitude of our terrestrial sphere. This also varies from -90 to +90, and this is also goes across for 24 hours, or 360 degree is traveled in 24 hours. So we typically express right ascension in terms of hours, minutes and seconds, and we typically express declination in terms of degree arc minutes and arc seconds. Okay, so that's the difference between the two. Typically you see this as referred to as degree, minutes and arc seconds, like that. And of course plus or minus depending on which side of the equator that particular source is located. So how do we go about doing this? So let's first define the hour angle and the declination, and from hour angle we will come to the RA also. So from the declination is basically it's just the distance. Suppose there is a source of cosmic source at the location X on the celestial sphere. Now the delta is basically the angular distance between. So and then so if we draw the a meridian passing through X, intersecting at the north celestial pole and the south celestial pole, you draw an imaginary line which passing through that location X of that cosmic source. So the so declination is the angular separation between the interception of X on that meridian and the intercept of the meridian with the celestial equator. That distance is known as the declination. What about the hour angle? The hour angle is the angular separation between this meridian, the meridian which is passing through X, and the meridian which is passing through the zenith of the observer at a given position. So that celestial meridian and this location, the angular separation between these two is called the hour angle. Okay, also defined in terms of hours, minutes and second, like the RA. Now, supposedly, so if this is hour angle and declination. So declination is universal, that is fine, because it depends on the meridian which is passing through the source. But hour angle again becomes relative to the location of the particular observer, because it is measure of the angular separation between the two longitudes or celestial meridian and the meridian passing through this source, where celestial meridian is depending on the zenith of the observer, right? So let us try to remove that also. For that, we need to choose a reference point. What do we choose? we choose the vernal equinox as the fixed point. So the point where the vernal equinox happens on the celestial equator, that point is chosen as the reference point. So if that is the case, then yeah, so it's analogous. So right ascension is analogous to longitude and is measured eastward along the celestial equator from the vernal equinox point of this kind of a distorted gamma, you can say, to its intersection with the object's hour circle. So right ascension becomes 0 on this, and then it starts counting eastwards in hours. And so it comes back and makes the entire revolution, and it goes back to 24 hours just before meeting the same point. Okay, so clear? So what did we do? Just a recap of that again. What we did is we defined few points. We defined first the declination, which started from locating the source X on the celestial sphere, and you draw an imaginary meridian passing from the north celestial pole to the south celestial pole, passing through X. Very good. So the angular separation between that point where X lies and the intersection of this meridian with the equator, that angular separation of both is known as the declination. And the angular separation between this meridian, which is passing through X, and the meridian, which is the local meridian, which is passing through the zenith of the observer, the angular separation between those two meridians is known as the hour angle. So when for example, if the source is passing through the zenith, then its hour angle will be equals to 0, right? So the other thing is, so basically now we have defined the declination, which is not dependent on the position of the observer, and we have defined the hour angle, but hour angle is still with respect to the position of the observer. So to remove that observer specific position, we define a reference point. The reference point is the vernal equinox point, from where the sun starts moving along the ecliptic towards north. That position where it intercepts the celestial equator, that position is treated. So when the meridian is passing through that vernal equinox point, it's known as the 0 hour line. So as it moves eastwards, the array goes from 0 to 1, 2, 3, 4. Like this, it covers the entire sphere and comes back to 24 hours. Okay. So that's how we define the array and the declination, and that becomes more universally acceptable coordinate system. So we define array and dec as the equatorial coordinate system, or alpha and delta. Now the advantage is that since the equatorial coordinate system is based on celestial equator and vernal equinox, changes in the latitude longitude of the observer do not affect the values of right ascension and declination. They are similarly unaffected by the annual motion of the earth around the sun. Okay, so we have successfully have defined a coordinate system which doesn't depend on the position of the observer. So we now define another most important thing, which is the local sidereal time. Now let us stick to the previous thing. So what we defined in the previous slide is that we defined the fixed point of the vernal equinox when the sun is going northward on the ecliptic. That point is fixed, and the meridian which is passing through that particular point is defined under 0 RA. So we also define local sidereal time to be 0 hours when the vernal equinox is on the observer's local meridian. Okay, so when the observer's local meridian matches, contains the, so supposedly we look into this meridian which is passing through the vernal equinox. So if this becomes the observer's local meridian passing through the zenith, then there the local sidereal time is counted to be equal to 0. So if you do all the math, the relationship which we can come up with is our angle is LST minus RA, or the right ascension. So a couple of important things is when any source is passing through the local meridian, then our angle is equal to 0. Our angle is 0 at local meridian crossing. This location is also very importantly called the transit. We will come to that. That is our angle equal to 0. That basically implies that LST is equal to the RA of the source. This is number 1, case number 1. Case number 2 is the hour angle of the vernal equinox. So at vernal equinox, RA is defined to be 0, right? So then LST is equal to our angle at the vernal equinox point. Okay, so 2 things to remember. First one is very powerful, I will tell you why, and the second one is also important to remember the difference between these 2. I will not go in details, but you can definitely transform from the one we learned so far, the 2 things, horizon to hour frame, and transformation from the hour to the equatorial frame. You can do that, both of them. So hour frame is that intermediate one, which has the hour angle and declination, and then hour angle of declination to. So this is the horizon, which is known defined by the theta phi, or the elevation and azimuth, also called the altitude. It is known as defined as h by the altitude and azimuth. This also is there, and from there to the hour angle and delta, and this one is going from hour angle and delta to RA delta or alpha delta, no matter what however you define that. Okay, so you can go through this. These transformations are best remembered as it is. There is a little less to be explained, so we skip to the next slide. So, very well. So basically, now what we discussed in that sphere, from the observer point of view, we don't see a sphere. We just see a hemisphere, the sky above us. Supposedly, you have your observer and you point your telescope, as a nice thing taken from the Calgary website. There is the reference in the next slide to the sun. And so if you point your telescope in the north-south direction, so you essentially choose a north-south geographic north-south location, and you draw the imaginary line connecting this. This is your local meridian. Okay, this is known as your local meridian. This is the line, and that line crosses through the zenith of the local position, right? So you have a celestial body which is kind of has its own motion. Supposedly, so it is moving from the east to the west. So it is moving, the celestial body is moving in this direction. The intersection of the celestial body, this motion, on the local meridian, this location is called transit. This is the place where our angle is equal to 0, which implies that at that particular location the RA is given by the local sidereal time, or vice versa. Okay. So supposedly we are in the northern hemisphere. Say I just take my location near Indore. It is 22 point something. I just define this as 22 degree north. That's the zenith. So you can see this is a different thing from Canada. So you can have a little bit more this thing. So you can see this these lines which are passing through and meeting the east-west. These are the constant declination lines, right? So the source also is passing through a constant declination line. So the source rises in the east and setting towards the west, passes through this blue line. If you have any other location, you can just point towards the north or the south, and you will see these constant lines of declination, and this individual great circles moving across in different. So apart from this line, there are other lines which are also going from north and south, but not cutting through the zenith. And those will also be seen here. This is a small, this is the web from where we collected the previous two pictures also, and nice. So you can, if your observer is looking towards this hemisphere, you can see the sky moving across. This is not with respect to that position we were talking about. So I am an Indore, so I will take roughly 22 degree north as the zenith point and do some further calculation. So because I am in the 22 degree north, so the zenith declination is also equal to 22 degree, right? So the declination of the source which is passing through the zenith is equal to delta equal to 22 degree north. That source will exactly rise from the east and goes to the west and pass through the zenith. However, there are other sources which can rise a little bit south, like this blue line, and also go and cut the zenith and meet somewhere here and further. So, because I am in 22 degree north, there will be the north celestial pole which will be visible to me at an exact elevation of 22 degree from the horizon. These are the lines which is representing the horizon. Okay, so if I look towards the north, then I would see the north celestial pole. Okay, what else? Any source which passes through the meridian, at the meridian crossing, those lines are called transits. Okay, that is the maximum elevation a source can have when moving through the sky. All right. What else we can do? Yeah. So depending on, so supposedly, if we are in the latitude of 22 degree north, my south celestial pole will be below the horizon always by about 22 degrees. So if you are at this location, you will not be able to see the south celestial pole. So just by this very efficient diagram, we can do a huge number of calculations and learn a lot of things. So what have we learned? We have learned about zenith. We have learned about transit. This is the maximum elevation point of a source. Source meaning cosmic source. Okay. What else we can learn? We have learned that if your latitude, if the source the latitude of the position matches with the declination of a source, then that source transits through the zenith of the observer. Okay, another powerful definition. So with that, we move ahead. We will discuss further these concepts in more examples. Okay. Another coordinate system we wanted to define was the galactic coordinate system. Very widely used initially because a lot of the sources were from the galactic origin. So the source localizations were almost in the galactic plane. So that's where we started from. So we just briefly discuss this. So it is a projected coordinate system where the sphere, the equator is in the galactic plane, and that is defined as the galactic plane, and the longitude increases counterclockwise from the galactic center. Okay, the angles, the direction of the north and the south galactic poles are there. Galaxy in a galactic plane looks like it's almost in near the equator. It's located. So that's the projected map. Yeah. So that's the galactic coordinate system, which is mostly based on the galactic, our own galaxy, and there are few transformations from the equatorial to galactic plane. First, let us understand the few details of the galactic plane. So, galactic longitude ranges from 0 to 360. Latitude goes from plus 90 degree to the negative 90 degree and south pole. Galactic center is located at the L equal to 0 degree, and galactic midplane is at B equal to 0 degree. Sun is the origin. Okay. So we can you can see how we transform the local the horizon system to HA, which is already we have seen the horizon system to HA and delta, and galactic and equatorial system. So if you have the galactic system of L and B, how do we interchange that with alpha and delta? By this. Let's take up one example to end this discussion. A pair of astronomers learns of an interesting radio source at a location in the sky given by RA equal to 12 hour, 30 minutes and 0 seconds and declination equal to 0. The astronomers decide to check it out and so set out to observe it with their own telescope, which is located at a longitude of 75 degree west and latitude of 35 degree north. They first check their computer and see that the current LST at telescope is 3 hours. So what are the following quantities? The RA and dec of the astronomer's zenith. What is the current hour angle of the radio source? Is the radio source above or below the horizon this time? What will be the azimuth and altitude of the desired sky location when it rises, and what is the azimuth and altitude of the desired sky location as it transits? So quite a few. So RA of the zenith at a given time is equal to the LST corresponding to that moment. So because our angle is equal to 0 at the transit. So declination of an observer is observer's zenith is the same as the observer's latitude. So the corresponding zenith corresponds to delta equal to 35 degree, and our RA is this. That's easy. The hour angle is easily calculated by subtracting the RA from the LST of the target source. So if you know that LST of the target source, then you can calculate the hour angle to be equal to this. At a given time. Altitude, you can put the value. So zenith, declination of the zenith is known, and the declination of the sky position is also known. So altitude is 55 degree. So we come to the end of this particular lecture, and we will continue discussing the coordinate systems, some more examples of it in the next class. One lecture after the next class. As you know that we have this material is available in multiple places. We have particularly used the book of Roy and Clark, and also some notes from Sarah Spoler, as well as the two hyperlinks we have given in the slides itself. So thank you very much for joining us for this lecture. We will see you in the next lecture as well. Thanks a lot. Bye.